All right. There you go. Okay. Hello. My name is Miguel Torres Gonzalez. I am here for the final project with Xflir5. This is for fundamentals of aerodynamics with Osby. Um, right now, we're going to focus on analysis of a wing. Um, this wing will have an aspect ratio of 10 and a taper ratio of 1, meaning it's a rectangular wing. So there's no taper within the wing. Okay. So yeah, let's get started. To get started, I'll click on Module and go to Direct Foil Design. And in here, I will input the airfoil the wing's gonna be made out of. You could click here in Foil and neck airfoils, or you could click Alt N like this, and you input your airfoil. So for this assignment, we're gonna be doing 2415. And number of panels, I'll do like 150. This will work just fine. There you go. And click OK. And now we have our airfoil in here. We have to go down and then go into Xfoil Direct Analysis. Click on that. And here we have to, like, before we do wing analysis, we have to do analysis of the airfoil. So in here we're just gonna do just like how we did in a previous project for the class. We're gonna just do analysis, and we could do a batch analysis or define analysis. I just do batch just so we have many data points. And it's important that you have a Reynolds number that corresponds to the wing simulation. In this case, it would be this Reynolds number right here. This Reynolds number is what corresponds to the actual simulation. So if we were to calculate our Reynolds number of the airfoil, which this would be, yeah, we would get this Reynolds number right here because our chord would be 1, and then of course we have our parameters. So yep, make sure you have that. You have to specify angles of attack. In this project, we'll be doing -5 to 15 degrees at increment of 1. And yeah, and then of course you could specify your threads to speed up the process, but you know, this is relatively easy to run. So click analyze. I'm gonna close it. And here you can see your data. It's at several angles of attack. And yeah, but we're focused on the wing analysis, so we're gonna jump straight into that. Now go back to module, and then here you're gonna go to wing and plane design. Click here, and then now you'll have to create a plane. So define a new plane, or you can press F3 right here. And I'll just change the name AR, let's say equal to 10 rectangular. There you go. Remove the elevator and fin. We're just gonna be analyzing the wing. And then in here, main wing, you have to click define. Now in here, this is where you're gonna have to change the properties of the wing. So first, you can just click here just to import your airfoil. Okay, all you have to do is just click and select your airfoil. And that's it. And then in our case, we're gonna be focusing on aspect ratio of 10 and have it be rectangular. So for that, we're gonna have a y. First one will be equal to 1. I mean 0. This is our root. And for 2, airfoil 2, we're gonna set this to 5. Just keep in mind it's mirroring it. So 0 to 5, and then later copy the same thing to the other side. So wingspan will just be 10. And we change our chord to 1 on both sides. I mean, yeah, both the wing and tips. Then we get our the geometry we want. Of course, we're going to change the offset here to make it truly rectangular. Remove the taper, because yeah, this is very important. If you have, like I had before, we can see that it's not going to really be rectangular. It really is not. So if I do this, yeah, root to tip sweep, you don't really want that. It has to be rectangular. So our offset will be 0 right here. This all looks good. No twist. We don't want any washout. And number of panels is where you could change the resolution. So I change the color here and have you see the panels. You can see how the panels change in resolution right here. I'll just do 20 for all of them right here. And there you go. And this looks good. So now we save it. And then now we save our wing. To see a wing, you go up here. There's this little icon with a plane in it. Click on that. And here you can see our wing. Now, before we analyze, we have to define the analysis. So in here, first things first, before you define the analysis, check on advanced settings. These are so we're gonna be using the lifting line method. But in here, this will be very important. This is basically like your residuals and answers right here, and then of course your max iterations. So you want to keep these like a lower number. If you have it a little bit too high of a number, then it will converge very quickly, and you're gonna get pretty inaccurate results. These are the settings I run, just 400 iterations, 1e to the -5 on alpha precision, and these two I just left alone. Yeah, if you do an analysis and then you find that your result is wrong, you might want to play with this a little bit. But yeah, so it goes, yeah. But go back to analysis, and we're gonna do define an analysis. In here, this is where we're gonna define our, our velocity. So we're gonna do fixed speed in here, and for our project, we'll do 50 meters a second. Then go back to analysis and make sure LTT is on. This is for wing only. This is what we're gonna be using for our analysis. And yeah, this all looks good. We don't really have to play with these for our project. Just leave that default. And yeah, now we save it. There you go. And now in analysis settings, this is where we set a sequence of angles of attack we want to analyze. So to start, we can go -5 and then later to 15 degrees. And increments right here, this will be just 1. And now we click analyze right here. There you go. Just very quick. And then yeah, now we got our results. You can see here, you can see our lift. This is at -5 degrees, so it's lifting down. If we go to 0, you see it's lifting up. And it's showing, like that. Yeah. And yeah, this is a behavior that's pretty typical right here. Of course, you see as there's higher angles attack, the higher the lift, and also you can see our center of pressure moving up in higher angles of attack. So yeah, this looks good. And yeah, now we're gonna go back to, you have to go through these graphs. And here we're gonna be using these two. These ones are for stability. We don't really need these. And in here, this is where we get our plots. CL over alpha, CD over alpha, CL over CD over alpha, and then we get our efficiency over alpha. This looks very typical. This is what we expect right here. And if you need to change your graph, just double click on the graph and select the variable and x-axis. And now if we go in here, this is where we get our span-wise parameters. We get our parameters along the span. So right now we have CL over the span of the wing, which would end at 5 right here. And if we double click local lift coefficient, we could also check induced angle right here. Then we can check our induced drag coefficient right here. And then, as you can see, an induced drag coefficient kind of tips down towards the wingtips. This is probably because at the wingtips we start getting vortices. But yeah. Of course, we get total drag coefficient if you want that. And then here we could get, let's see, CL or CD along the wingspan. And yeah, that's pretty much all we need for the project. Of course, there's a bunch of other parameters here, but yeah, that's pretty much it. Let me see if that is really all of it we need for the wingspan. Induced angle of attack. Yep, we got that. Yeah, that's this. Induced drag coefficient, long span, we did that, and then local lift coefficient. So yeah, that's pretty much it for the assignment. Yeah, and see you later.